we are going back to the basics. Counting. How do we count? Well, and the reason why I'm doing this is because, well, we got to know how the computer represents numbers, how it stores numbers. It stores numbers with a little device called a transistor. Let me read this quote to you. This is from a letter to her mother in the 1840s. Lady Ada Lovelace speculated that Charles Babbage's analytical engine might act upon other things besides numbers. The engine might compose elaborate and scientific pieces of music of any degree of complexity or extent. Who knew that she was going to be such a visionary, right? But it's all about the numbers. Now, Charles Babbage's machine, it represented numbers, and he had tried all sorts of bases, but it represented numbers with base 10. It had these cylinders that turned, and because a cylinder has pretty much an infinite number of positions, he could have picked any base, and he had basically put the numbers 0 through 9 around each cylinder to represent a digit. Okay, now, why do we use base 10? Well, probably because of these guys, right? You know, we go 0, 1, and remember, and this is something you're going to hear me say over and over again, all good engineers start counting from 0. So, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we've filled them up, and so we need to increment the next highest digit, right? What was it about base 10, though? Well, the reason, probably because we have 10 fingers, right? Well, if you talk to an ancient Sumerian, that probably wouldn't have been the answer. They used base 12, base 60. Heck, some of the ancient civilizations used base 144. Well, I don't really have 144 anything. Heck, I don't even have 144 hairs on my head. How did they use those bases? Well, it turned out that they used their fingers still, except they used it in a slightly different way. What they did was they used their thumb as a stylus and basically pointed at the segments or joints of the segments of their fingers. So we had 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Now, that makes sense for base 12. It could possibly even make sense for a base 24, possibly, but that wasn't how they used this left hand. Base 60 was done more along the lines of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and they put a finger, they raised one of the fingers on their left hand to indicate they had gone through this hand one time, and then they went 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and had a second finger, so they could count through it 5 times, count through their right hand joints 5 times, and get 60. 144? Well, 144 would have been something more along the lines of using the joints on their right hand to count through the ones place, so to speak, and then count through the joints on their left hand for the 12s position. Think about it this way. What you've got are 2 digits, right? And in our standard base 10, what we do is this is the ones place, this is the tens place, right? And another way of looking at that is this is the 10 to the 0 place, this is the 10 to the 1 place. Well, if you have the 2 hands, what you're looking at, and counting the joints, what you're looking at is this is the ones place, this is the 12s place, corresponding to 12 to the 0, and 12 to the 1, right? Okay, now, so we've got this digit, right, the ones place, this digit, the 12s place. Computers don't count with their fingers. They don't have joints and so forth. What do they count on? They count on a little device called a transistor, which is put into a binary state. So you've got some sort of positive voltage here. You got some sort of a control input here. And what you can do is from here, you read at this point either a 1 or a 0, right? That's the way they count. is with these digits. Now, what you do is you put one of these digits to represent the ones place. But now, how many possible values can this digit have? Well, 0 or 1, there's 2 digits, so it represents its digits, once again, with the ones place in the least significant position. This is the 2 to the 0 position. This position right here is the 2's place, so to speak, 2 to the 1 position. This position right here is the 4's place, representing 2 to the 2. This position right here is the 8's place, 2 to the 3. All right. Now, pretend our fingers are transistors. We've got them down, that's a 0. Up, that's a 1, right? And so I have 10 transistors, so to speak. They're either on or they're off, okay? So the way we count is to go 0, 1, 2, 3, 4, 5, 6, 7, 8, and so on. So how high can we count with our fingers? Well, if we look at our fingers as on-off Boolean devices, each one of them can basically represent a 0 or a 1. We've got from all zeros, right, to all ones. How many digits is that? Well, let's take a look. Let's instead draw a representation of our transistor. Sorry about the pen. We'll do it with, let's see, 10 digits, right? All right, so we've got all 10 digits there. This is the 1's place, the 2's place, the 4's place, the 8's place, the 16's place, the 32, 64, 128, 256, 512, okay? So those are the fingers, right? So we've got all of our fingers representing those positions. Well, if we were to perhaps turn on or, enable or activate say the 1's position, the 8's position, and the 16's position. Well, what that would give us is 16 plus 8 plus 1. That'd be 25, 24, 25, okay? So what's the highest number I can count to on my hands? Is it 10? No. Is it 12? No. Is it 60? No. Is it 144? No. What is it? If all 10 of these are active, then what we have is 1 plus 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus 128 plus 256 plus 512. That's 1,023. So if I basically put a 1 or activate every one of these, what the computer reads this as is 1,023. Another way of looking at this is that if I had an 11th finger, okay, if I were to add 1 to this, turns all of these 1s to 0s, and puts a 1 in this position. What's that position? That position is the 1024 position. That's the 1024 position. Then 1 less than that is 1,023. And so this is how the computer uses its transistors, its fingers, its digits, so to speak, in order to count in binary.